Welcome to the JewelBox demonstration. Introducing Paul.
Hi guys, I'm Paul Delano. I'm with Ecogen Energy, and this is the JewelBox. What I'm going to be demonstrating is the 20 kilowatt JewelBox. The primary difference between this and the 60 kilowatt is the 60 kilowatt is about 6 inches wider. Now, we start out with the lithium-ion battery brick. What is unique about this is it is wired together both in series and in parallel, so it can continuously charge and discharge. What that means is that we can operate it at 100% charge at all times and not use up the 5,000 charge-discharge life cycle. Because of that, this will have a useful life of 20.9 years.
Jeez.
Long time for a battery.
Right.
Yeah. Now, we need this because we're constantly pulling from this battery to send pulses into the star motor. And that's our patented star motor. Come over here and I'll show you this. Now, this is the inside of the star motor. And it's a 6-4 switch reluctance permanent magnet motor. The key here is we're trying to produce more horsepower without putting more watts into it. And you can see from the formula for horsepower is torque times RPM divided by 5252. Nothing in there says anything about what's the watts in, what's the watts out. It's how can we create more torque and how can we get more RPM? Well, you get more torque by being as close to maximum saturation of the core as possible, which is 20,000 Gauss. Now, the permanent magnets that we have in here have a Gauss field of 15,000 Gauss. Gauss is, of course, the measurement of the magnetic field. So, all we have to do is to add 5,000 more Gauss, and we're pretty close to maximum saturation.
Yep.
We do that by pulling 8,000 watts in pulses from the battery into the coils. Now, this is all made up of electrical steel laminations. And if you look on that has little white lines on it.
Yep, I can see them.
That are made up of silicon, because the magnetic field doesn't penetrate into the steel.
Right.
It is carried on the surface. So what we want to do is increase the surface area, and you can see these are all cut out the exact same shape, and we glue together in a lamination stack over 1,000 of these. So we've increased the size of the magnetic field considerably.
Sure. Yeah.
Right. Now, we then do our coils that are wrapped around this crossbar. Now, this crossbar has insulation on it, and this is the coil, and this just slides right down in there.
Yeah. Yeah.
And you can feel how heavy that is.
Oh, jeez. That's some thick winding.
Yeah.
Oh, okay.
Okay.
Yep.
Well, what I always say is when you're dealing with energy, it's E equals MC squared. The M is mass. You've got to have mass.
Right.
Okay. Now, one of the keys to this motor is its bifurcated stator, which is a split stator. We have 6 stator poles. This is 1, 2, 3, and then 4, 5, 6.
Yeah.
And then in between each one, we have the permanent magnets. And the coils are wrapped on each one of these. Now, these permanent magnets, here's some. These are N50 neodymium permanent magnets. You're more than welcome to try and pull them apart. I can take them with all my strength and not budge it. Because each one of these is strong enough to pick up 1,000 pounds. So between those two, I've got this wood piece here, to keep them separated. Otherwise, I could never get them apart.
yeah.
Because each one is strong enough to pick up 1,000 pounds. Here, just saying, I'll show it to you. Just getting it close to something. And it just grabs hold of it. Then the key is you slide it off. And that's a lot easier than pulling it off. Okay? So just getting it close, it just grabs hold of anything that is magnetic. Now, my timing disc, which is the same shape as my 4-pole rotor. When this point is right in the middle of the V, of the bifurcated or split stator, that's when I send the charge into the coil from the battery. And the magnetic coil flux travels down the stator arm. Now you saw what it did with the magnet. When it's within a foot, it just grabs hold of it. This is right next to it. It's instantaneous. It just grabs hold of it, and that dual flux comes into the rotor, and that causes this to turn. That's what gives us the torque, which is what we want here. More torque. Now, if I just left the charge on, then this pole would line up with the stator pole and it would just lock down. But this slot tells my controller that can handle 3 million instructions per second to turn the charge off. That's going to release this, and the rotor is going to keep on turning. Now, when that takes place, the back EMF is going to want to go back into the coil. When you put watts in, it is not watts in and watts out. It's watts in converted to EMF, or electromotive force, that's going to cause it to turn. And wherever you have EMF, Lenz's law says you have an equal and opposite back EMF. So it takes the same amount of energy to stretch a rubber band out as it does to pull it back. Now, the back EMF wants to go back into the coil, but I created this crossbar, and there's insulation, so that's going to restrict it from going back into the coil. And I've got this magnet pushing it this way, and I've got this magnet pulling it this way. So it comes up, crosses over, comes to here, where it can be used by the next coil. And then the next, and the next, and the next. And it just keeps on going round and round. Now, I've had people ask how long this is going to last. By the time we could show Lloyd's of London, who provides our manufacturer's warranty and guarantee, that it's going to last for 40 years or more. And there's no major parts that are going to need to be replaced for 20 years. That's when they agreed to insure it for 10. Okay. Yeah, so the bearings, these are only going to last for about 10 years under normal wear and tear. But most of the wear and tear takes place on the start-stop. We can just run these continuously, and I've got some of my lubrication guys that have said that we can put special lubricants in here that'll have these last for 30 years time. So most manufacturers don't want it to last for 30 years time. What they want to do is to replace the parts, but I just as soon have it just run and run and run. Okay? Now, because we redirect the back EMF, we don't have that heat buildup and the resistance that is caused by the back EMF. You can see here, this is a thermal photograph that was taken prior to operations. And we're at about 27 C. After it's been running for 45 minutes under load, we got up to 29 C.
2 degrees.
Which is nothing.
Nothing.
Nothing. every conventional motor is going to be up around 100, 125 C. And so we have been able to keep that heat down, and because we're just pushing it around and around and around. So we don't have the resistance.
Yeah.
Make sense?
Yeah, so,
Okay.